This is Bob McFetrich with Beckwith Electric Company, and I'd like to welcome you to Session 1 of our Integrated Volt-VAR Control Seminar. In this session, we hope to present different business and economic drivers as to why a utility may want to look at IVVC as a future project. So, again, and we covered this in the introduction a little bit, but IVVC is Integrated Volt-VAR Control, and the goal is to control the distribution voltage in a coordinated manner using a combination of regulator and LTC low tap changer transformers along with switched capacitor banks downstream. And the overall goal is to, first of all, be able to flatten the voltage on the distribution circuits so that we can get additional reduction of the voltage, and by reducing voltage be able to reduce the load. So in other words, it gives the utility a way of dynamically being able to reduce the load when needed. The other goal we're going to try to do with this is to try to reduce operations on our equipment that's more expensive, such as the low tap changing transformers. Finally, by having the capacitor banks regulating the voltage with the regulators, we hope to have a better power factor and therefore reduce the line losses, which will free up capacity. So those are the overall goals that we're going to be talking about today. And to do so, first of all, we have to look at the dynamics of the utility. So some utilities are generation only, some are transmission only, some are distribution only, and a lot of the investor-owned utilities may be a combination of two, if not all three. So we have customers like municipals and electrical cooperatives that would typically be distribution only, or they may own a little bit of transmission or a little bit of generation. Then we have our deregulated utilities in the Northeast that are typically a distribution company and then also broken down into a transmission company. And then we also have transmission companies as part of ISOs. And then finally we have our generation, which could be a visitor-owned utility running a power plant, or it could be a for-profit company, either as part of DG or as part of the deregulated environment that's running the company. So we've got to look at the economic goals for each of the three. So, if you are in generation, just say you are an investor-owned utility and you own your own generation. One of the things that IVVC allows is the ability to reduce the load on demand. And that can have two major impacts for an investor-owned. One would be to reduce the system peak. As we know, a utility must have enough reserve generation capacity to support the system peak plus a certain percentage on top of that. So if we can reduce the system peak, we can reduce the amount of reserve capacity required. So if a utility is reaching the maximum limits of the existing reserve capacity, then they would have to look at constructing another power plant, typically a peaker plant, to be able to support that additional reserve capacity required for the new peak. The other way we can do it is on a daily basis by reducing the peak at any given time. So as a utility has load coming on, it has to have the generation resources to support that additional load. If a utility has all its base load units, which are typically coal-fired plants and nuclear plants that produce the cheapest energy, if those plants are all online and additional energy is still required, a utility would typically have to bring online a more expensive plant, such as a gas or fossil fuel plant. And this gas plant would be more expensive to operate. And also, in all likelihood, this peak may only be there for 10 or 15 minutes. So you're bringing a plant online for a very short period of time, which can be an expensive proposition. So again, if I can lower that demand for that period of time and not be required to bring that additional unit online to have the spinning reserves, then that would be a benefit to the utility. Another benefit may be in the area of carbon tax and just political correctness. A lot of utilities are facing scrutiny from the public on the CO2 emissions from particularly coal plants. And there is the possibility for carbon tax credits. So the greenest power that can be produced is not nuclear or wind or hydro or solar, but it's the power that never needed to be produced in the first place. So every megawatt we conserve is 1 megawatt we don't need to generate for. And therefore that may give us the abilities in the future to have carbon tax credits or DG credits. Another area where states are regulating on utilities is the amount of distributed generation required on their system. In some states it may be as high as 20 to 30% by the 2020. DG has some major disadvantages right now in that, first of all, it's typically not controllable by the investor-owned utility. So you are losing control of some of your assets. The other issue is that most of the DGs currently cannot supply voltage support or VARs onto the system. So in system emergencies, it is difficult to call on them to put megavars out onto the system to keep the voltage up. So for that reason, utilities tend to not like to have too much distributed generation on their system. So by being able to shave the peaks and conserve, you may be able to use that percentage as a percentage towards the percentage of DGs that you need to have on your system. Other problems coming up in generation is that it takes several years typically to bring a new plant online. And with the advent of all electric vehicles, if that demand continues to increase, it's going to put a lot more stress on the electrical system overall, and will need additional generation. And we don't want to get to a point where the load exceeds the amount of generation that can support that load. So with hybrids, they really didn't have any impact on the electrical system. But with the all-electric vehicles such as the Chevy Volt, those will be plugged into the electrical system to be charged, and therefore that will increase the demands and the need for generation, unless we can offset that increase of load with a decrease somewhere else. And as we discussed, retaining control of the system. DGs are not going to be under the control of the investor-owned. You don't know when they're going to be online. Several of them, wind and solar, can be very dynamic in the energy source. Cloudy days, they can go in and out, or as the wind picks up and dies down. So it's not a very reliable generation source, and typically it cannot support the voltage. So, in summary, for generation, it is good to be able to control the load to work around your units. So we don't want to have a high system peak that's going to require additional reserve capacity. And we may want to be able to dynamically, for short periods of time, reduce the load so that we don't have to either bring a more expensive unit online for a short period of time, or go out into the spot market and purchase power at a higher rate to fulfill that short-term need. And finally, with the DG and the electric vehicles coming up, we can see that the future is going to put stress on the generation overall. For transmission, it's a totally different goal. So, with transmission, if your utility is a deregulated utility and a transmission company only, the major goal you can gain with IVVC running below you at the distribution level is that reduced load at the distribution level translates into reduced capacity on the transmission level. Now, normally you're getting paid for that capacity, and you don't necessarily want to reduce it unless your assets are reaching their limits. It is very expensive to build transmission lines, very difficult to get them permitted. A lot of states have environmental rules as to where you can run transmission lines, and in a lot of states they can only be within so much distance of schools and of churches and other public buildings. So it's becoming much more expensive and harder, and therefore time consuming, to construct transmission lines. So if my lines are starting to exceed their rating, I either need to be able to decrease the load on the distribution and thus decrease the load on my transmission lines, or I have to be able to build new lines to support that demand. Security is another issue at the transmission level. The last few blackouts have not been caused by frequency, but have been caused by voltage due to a lack of VAR support. And a lot of the DGs that are coming online are not helping with the VARs. So as the voltage starts to dip on the transmission system, if we can reduce the load for a short period of time, that may allow the voltage to remain stable until we can get additional generation on board or additional VARs on board to stabilize the voltage. So by having the ability to reduce the loading at the distribution level, it can help us keep the grid up on the transmission level to avoid brownouts and blackouts and give us more time for VAR support. The other advantage is it can reduce the need for VARs to flow from the generator to the distribution. So VARs can only be generated by two sources: generators or capacitor banks. The consumption of VARs is done at the motor load, that typically at the distribution level. So if we can run unity power factor or even slightly leading power factor at the distribution level, we can have all the VARs that the load requires being supplied at the distribution level, and therefore not needing to go across the transmission grid from the generator to get to the distribution level. This saving of VAR flows then allows for more real power to flow through those same transmission lines. So if we can reduce the amount of VAR flow or become VAR neutral to the transmission grid at the distribution grid level, then we can focus on transmitting more real power through the transmission lines. Finally, at the distribution level, a reduction in load, first of all, will reduce the carrying charges from the transmission grid if you are a deregulated utility. So if you're a deregulated distribution company, you have to get your generation through the transmission grid, and your transmission provider will charge you a carrying charge for carrying that power through the transmission grid. So the less power that's going through the transmission grid, the less that charge will be. So if we can reduce our distribution load, we can reduce the transmission charges. If we can correct the power factor closer to the load, as we just discussed, we can reduce the losses on the distribution grid also. These reduced losses, just as on the transmission grid, will then free up capacity on our substation transformers and on our feeder circuits to carry additional real load, which is revenue generating. So if we can reduce the losses, we can reduce the VAR flow, therefore allowing for more real power to go through. And transformers which have an MVA rating, the less VARs that they're carrying, the more watts they can carry. So as we reduce voltage, we reduce load, but we also reduce losses, and those losses can free up capacity, which can allow us to delay expenditures. So if I had substation distribution transformers, maybe they're 230 to 25 kV, and if they're 40 MVA and they're starting to reach that limit, I will either have to replace those with larger transformers, or I will have to put in an additional transformer, or the third option is to try to reduce the load so that I don't have to do either, thus saving capital expenditures. I can also reduce operating costs. One of our goals with integrated volt VAR control is to try to take operations off of more expensive equipment such as load tap changing transformers and feeder and line regulators, and place those operations on less expensive equipment, mainly capacitor banks. Especially with LTCs, if we can reduce the number of operations, we can reduce the maintenance cycles. And with transformers continuing to increase in their capacity and reaching near capacity, it's becoming much more difficult for utilities to take them out of service to perform maintenance on the LTCs. So if we can reduce the maintenance cycles on LTCs, then we can also reduce the amount of labor required to do both the actual maintenance itself, but more importantly, the switching required to get that transformer out of service. So we can reduce a lot of operations and maintenance costs. Also, by reducing operations, we can extend the lifetime of that equipment. So, if you're an electrical cooperative, your financial or economic drivers are going to be several. First of all, your charter is to be a nonprofit and provide electricity as safely, reliably, and economically as possible to your consumers. So if we can reduce load full-time by reducing voltage, we are reducing your customer's bill and you are meeting your charter. We can also reduce the amount of operations on your equipment, which is good for you in reducing your OEM costs. And also, by extending the life of some of this equipment, reducing your capital costs. If we can reduce the load and you are being charged a transmission fee, then we can reduce that transmission fee that you're currently paying to your transmission supplier. Also, if your charges from the investor-owned or your energy provider are off of peaks, by shaving the peak, we can reduce your overall load or your overall bill. And finally, by reducing our losses by having the capacitor banks, we can increase the availability of your overall system so that you can get more real power through that system to your end consumers. For an investor-owned utility that owns the distribution companies, a lot of the same economic drivers are available. We are going to reduce operations and therefore maintenance cycles and costs and extending lifetime equipment. We are going to reduce line losses, therefore increasing the availability. We are going to be able to reduce load, therefore reducing any transmission charges if you are deregulated and have to pay those to a deregulated transmission company. Another thing we can talk about is DG. We know that distribution generation is going to be coming on board, and it is going to affect the voltages and the way you regulate the voltages on your system. And by having an integrated volt VAR control system in place, you'll have more flexibility on incorporating the DGs when they do come into play. If you are an investor-owned that is not deregulated and you have all three areas within your control, generation, transmission, and distribution, then your goals are more on the generation side to start with, by reducing the system peaks and therefore reducing reserve capacities, reducing short-term peaks so that we can reduce spinning reserves, reducing load in system emergency conditions, being able to hit one button and have 200 or 300 megawatts come off your system could very much be beneficial if we have a voltage collapse. Reduction in operation of apparatus, Also, reduction in CO2 and possibly carbon tax credits. Reduction in load means that we can free up some transmission capacity. So if we have certain areas of your territory where your transmission is really being saturated, we can do a area-wide IVVC. Instead of a system-wide, we could target specific areas to reduce the amount of transmission carrying capabilities required for those areas so that we could possibly delay constructing a new transmission line by a few years. So I hope this is giving you a general idea of some of the economic and business drivers that may impact your utility. But in summary, the major goals are, first of all, to have the ability to reduce your system peak. That can help you in either reserve capacity or in billing with your energy supplier. Also, the ability to reduce load dynamically. Again, to allow generators not to have to come online for short periods of time can be very beneficial. Reducing line losses that will free up more capacity to transmit and deliver real power as opposed to reactive power, and therefore reducing the VAR requirements on the transmission grid. So those are some of the core things. We have added benefits such as reducing the CO2, possibly getting carbon tax credits, reducing the operations on some of our higher priced equipment and therefore delaying maintenance cycles and extending lifetime of equipment. But the big ticket items are delaying capital expenditures, whether it's building a new power plant, whether it's building a new substation or building a new transmission line, or changing out a transformer from one size to a larger size. If we can delay capital expenditures by reducing voltage, we can receive economic satisfaction. So hopefully you've enjoyed this session and will join us for the next session, session 2, which is why do we need IVVC? We at Beckwith Electric, as always, very much appreciate your time and hope that you have a blessed day. Thank you.